My name is Nikhil. I work for MeteoGroup as a data scientist and a data engineer. My background is in computer science. Before, I used to work in the area of genomics and genetics, and now I'm in the domain of meteorology. Is it? Yeah, cool. Well, we have the screen now, thank God. So yeah, as I said, my name is Nikhil. I work for MeteoGroup as a data scientist and a data engineer. And today my talk is going to revolve around data science and engineering in the area of weather forecasting. Hopefully, after the talk, everybody in the room knows a thing or two more about weather forecasting. What's the agenda for today? I'm going to start with talking a bit about MeteoGroup and introduce briefly about weather data and describe the problem we are trying to solve and how we leverage data science and engineering to solve this particular problem. At the same time, we're going to do the verification of the model which we created, and then discuss about the lessons we've learned and what are the improvements. And at the end, I'll leave some time for questions, so please do ask questions. So before we jump in, same question which I asked before, how many of you check weather forecast frequently? Hands up. Awesome. So, rightfully so. Weather is pretty important in our daily lives. We want to plan something, be it going on a vacation or doing a weekend barbecue. We definitely want to look for how the weather is going to look for that particular duration. And that's what we do at MeteoGroup. At MeteoGroup, we are into weather forecasting, and we are the Europe's largest private sector weather service provider. We've been in business for the last 30 years. We are around 450 people big, and out of which 150 people are meteorologists. And we are founded back in 1986 in Netherlands. Right now, we are under the umbrella of General Atlantic. Our headquarters is located in London. Our presence is in more than 15 countries. The operational hubs are over here in Berlin and in Netherlands. Apart from doing daily forecasting, day-to-day information, we are also providing different businesses with useful information, especially helping them make better business decisions using weather data. Where does it really come into play? It really is very important in the form of predicting extreme weather events, be it hurricanes, tornadoes, or extreme winter storms. So apart from that, we are also present in the area of commercial shipping, offshore oil and gas exploration, road transport, and many more sectors. So we are definitely a data-driven company. We have around 200 different sources of data. It would be hard to talk about all the sources, but I try to categorize them into 5 buckets, and I'll just give you a brief introduction to each bucket. So we crunch around 1.5 terabytes of data per day. As I said, we have lots of sources. Again, this is exponentially increasing. The rule of thumb is that every 2 years, we double our data footprint. Types of data, to start with, we'll start with observations, which is the real observed value at the weather stations. We accumulate around lots of data from lots of weather stations, especially from WMO weather stations, which stands for World Meteorological Organizations. And the weather stations are located on different formats, actually. So not only surface weather stations, we have weather stations on balloons or aircrafts, even ships. And apart from that, we have our own MeteoGroup station network, which around 1,500 stations, and we also accumulate data from them. And the second type of data is satellite data. As you can imagine, it's mostly imagery, but it's very, very useful when we are trying to forecast precipitation or even like rain or snow. And the third type of data which we also accumulate is radar data. Again, this is also a big part, especially when we are trying to forecast cloud cover or how clear the skies are and what it's going to look like on that particular day. And we also have user data because we have clients all over the world on different sectors. To make them have a better decision, we have to get their data and try to find correlation between their data and the actual weather forecast, and then prescribe what to do on the next few days. And last, and the most important one, we have the numerical weather prediction model data. This is very complex and also multidimensional. So I'm going to spend a few minutes talking about it. Why did I say complex? When we're talking about numerical weather prediction models, if you take a numerical weather prediction model, they divide Earth into different atmospheric boxes. And for each box, they try to apply mathematical equations using current weather, and then try to forecast weather for next certain period. Where are these equations coming from? They're derived from laws of physics and fluid motion. So it makes really, really complex and important. And this data is also multidimensional. As I mentioned, they divide horizontally by atmospheric boxes, latitude and longitude, but also elevation data, which has data for different pressure levels. In general, we get data for around 91 pressure levels, but our forecasting system, we use around 10 different pressure levels to do the forecast daily. And we get the data from 5 different NWP models daily, and they are from different providers. And the data size per day is around 0.5 terabyte. So this is where, as a company, we play a significant part. If somebody is asking for your temperature for tomorrow or next few days, you can't just give them 0.5 terabyte of data, say like, forecast it yourself. So that's where our business lies in. We make it simple and human intuitive so that they can digest the information much more efficiently. So yeah. So how do we do it? Biggest part is using machine learning or data science and big data. Well, data science and big data have been the buzzwords last probably 5 or 6 years, which is nothing new in the area of meteorology. In fact, back in 1950s, when John von Neumann at Princeton came up with a numerical computer, ENIAC, one of the first challenges he tried to solve was doing weather forecasting, which was very interesting. So we came a long way after that. He tried to forecast weather for 24 hours, and it took him 24 hours to do it. So by the time he had these calculations, the 24-hour period was already passed. And the horizontal grid which he had was around 736 kilometers. And the results were pretty poor. It was not anywhere close to the real observations. After that, in last 60 years, we came a long way. Right now, the grid we have is around 16 kilometers for highest resolution. And even the results are much more closer to the actual observations. Now, at MeteoGroup, how do we digest all this information? 0.5 terabyte of data. We have lots of data from images, satellites and radar, and also from weather stations. So how do we do it? So if you look at this picture, you look at the Earth, which is divided into grid level. So for any location, which is a weather station, we try to mix the data from a numerical weather prediction model and then supply the observation data and come up with a high-quality weather station forecast. So to make it more understandable for people who are doing machine learning, we use historical data for around 3 years and supply it to the machine learning model along with the 3 years of observation data. And then train the model depending upon the input parameters and come up with a coefficients or trained model which accepts daily numerical weather prediction model data and comes up with a forecast. Again, this is a very simplified version of what we do. I'm going to talk in depth in next few slides. So at the core of MeteoGroup, we have a system called MeteoGroup Forecasting System, which has been there for a while. And it's written in Pascal, thousands and thousands of lines of code of Pascal. And it runs on in-house high-performance computing cluster. And every day we take around 30 minutes to, from end to end, supplying the data to the Pascal code and coming up with a forecast. And what are the limitations of this particular system? It's hard to maintain. It's been designed, again, a decade ago. Lots of people worked on it. They were trying to put all kind of band-aids over the years, and it became not so transparent. Very few people within the company understood what exactly it does, and it's not really scalable. As I said, and the data is significantly going up. Every 2 years, the data is doubling down. So to address these limitations, we thought we should redesign the entire system altogether. So before we thought we went on to designing the system, we thought what are the features we want to look into in the new system. So the first one was move the solution to the cloud from in-house cluster. As a company, we are transforming from running everything on in-house cluster to the Amazon cloud. We have around at least 10 to 15 products which are already running on AWS. And second thing is we really wanted to be transparent. What do you mean by transparency? If you're forecasting weather all over the world, and if it's really working in some part of the world and not in other parts of the world, we really want to know what are the reasons it's doing it. So that was another objective, and we really wanted to make it scalable. Last and but not least, improve the forecasting accuracy itself. Now, if you're rewriting the system altogether, we've thought we should also spend lots of time doing rethinking the machine learning part. So that's where we started. These days, data scientists, when you give them a problem, most of them jump directly into the advanced modeling. We thought we'll do something very, very simple. So we took the NWP data and tried to downscale the data to the locations and did lots of data wrangling work, especially removing the outliers and filling the missing values using basic interpolation techniques, and then came up with a simple linear model. And again, this started on a single guy's computer on a MacBook Pro, where the data is sitting on an S3 bucket and crunching it overnight. And we wanted to see how the results look like. The outcome, because we were doing basic simple modeling, it was very fast. Accuracy was not that great. And we observed lots of multicollinearity. So what does multicollinearity mean? If there are two features which are trying to influence the outcome in the similar way, the rule of thumb is generally they bring down the accuracy rather than take up the accuracy. So the first thing we wanted to do was to work on these problems and try to solve them. And how did we address the multicollinearity? We did basic feature selection using linear models. And then at the same time, we also wanted to scale the features. Now, why do we scale the features? If you take for a weather station for a given weather attribute, we have around 200 to 300 weather features. Now, most of them are in a different range. Let's say if you're talking about precipitation, most of the time it's 0, whereas you take the temperature, it's in the range from -15 to +30. So if there's a higher range, it's become sensitive to the other parameters which are on the same model. So we did address these features using scaling, and we did the scaling using soft normalization, and then fit it to the same linear model. What was the outcome for this particular thing? Obviously, once we removed the multicollinearity, we definitely saw a bit more accuracy within the model. And this was kind of encouraging. But till date, we didn't do anything complicated, no real advanced modeling. And then I walked into my boss and said, okay, this is very positive, so probably we should invest more resources. So we had a few more people working on it, and then we started doing a bit more advanced modeling. And the first thing we were planning on working was to do, along with the linear model, we wanted to see how complicated nonlinear models work. So we implemented a basic model selection algorithm, which was trying to see what's the distributions for that given weather attribute, and select, depending upon the pattern, a linear versus nonlinear model. Now, as I mentioned in a previous slide, we were doing basic linear feature selection. So if you're doing linear feature selection and then trying to feed it to the advanced modeling, which also includes nonlinear models, it doesn't really make sense because you're already removing lots of nonlinearity while doing the feature selection. So just because of these reasons, we have to rethink the feature selections as well. So we went back to the drawing board and implemented a bit more advanced feature selection, which included a random forest and vector machines. So once we got this thing up and running, what did we see? Surprisingly, the system was on par with the existing forecasting system. Even though we are not happy with accuracy, we wanted to invest a bit more resources into this particular product and see where we are going. And on the downside, the training was very, very slow. Obviously, when we are trying to fit kernels and do a bit more advanced modeling, it does take a lot more, it does require a lot more resources and include lots of training time. So we wanted to stop here and see, instead of doing it on a subset of stations, we want to see on how the model is behaving throughout the world. So that's when engineering came into the play. We did spend lots of time taking the product to the operation. We started with simple stack. We settled down with Python. We used scikit-learn for basic feature selection and NumPy for cleaning up the data. And we also used TensorFlow with Keras. So Keras with TensorFlow background for writing the model selection algorithm itself. And we Dockerized everything. And we were running this Docker container on a Mesos cluster. What was the good about it? Python machine learning ecosystem. It's very, very mature compared to many other languages. And it's very easy out-of-the-box algorithms, where you can try it out and see how the data looks. Familiarity among the team. If you take any team within the MeteoGroup, there are data scientists, meteorologists, and engineers. So it's really hard to find the common ground, especially in the engineering sector. So we, learning Python and making others really, to get them contributing, it was easy to settle down with Python. And we were definitely doing test-driven and agile development, which was not easy, especially with researchers, but still we ended up having tests for everything and then do the agile development. And the last and the most important one is failing fast. What this setup allowed us to do is, if you have an idea, it took very, very little time to implement the idea within the ecosystem and look the results immediately and see if it's really working or not working. From my experience, out of every 10 ideas we had, we only had one good idea. So, which is more often than not the case in the research. But this along came with a bad. What is a bad? It was not really scalable. Again, Python is primarily a single-threaded programming language. Again, you can always do multi-threading, but still, it's not high performance compared to writing in C or Pascal or even Fortran. So this is where we had to stop and say, like, oh, what are we going to do about scaling? We had two options. First one, to rewrite everything in low-level language, either in C or Java or even Pascal, or get this Docker container and simultaneously run it across multiple locations throughout the world. Well, how many locations we train for? We have 47,000 locations throughout the world, and we do predictions for 15 different weather attributes. Those are the core weather attributes we train for, and then we predict for 15 days, which is 360 hours. So that many number of model runs we are supposed to do. So even if you are taking around 15 minutes for each model run, we are talking about days to weeks to months. So that was a huge problem. So we went back and thought how we want to scale this particular product. So we were looking for a scheduling system which automatically runs on a bigger number of cluster. So we did evaluate few. One of them was Airflow, Apache Airflow, and the other ones we looked at is Luigi. It's from Spotify. But for this particular product, we thought using Airflow is a good choice, and it's an Apache product. To talk a bit about Airflow, it's by Airbnb. They open sourced it in 2015, and it was in Apache Incubator in early 2016. The basic pipeline, which you call as a DAG, which stands for Directed Acyclic Graph, which is nothing but a sequence of tasks which will run on a cluster. And it comes with the different UI components. One of the components is UI, user interface, where we can track or monitor the progress of the particular tasks. And there's a scheduler which looks for a new task within the infrastructure and then dumps it down to the executors which actually run the tasks. Bit more details into the Airflow infrastructure. Each job or pipeline, which is known as DAG, has different programming components. Hooks are nothing but which are the connections which establish connections between different modules. Per se, you have a job which is trying to move data from a S3 bucket to a HDFS. So you obviously have to maintain the connections between S3 and HDFS. So hooks are the one which will process the connections. Operators are the actual tasks which do the job. And schedule is the one how frequently you want to run the job. From my experience, you can run it from days or months to given hours or seconds. And then you can also define the dependencies between different tasks. Let's say you want to run on task 2 after task 1. So you can do that too. So we took the Docker container and we've decided to run on the Mesos cluster, which is built in within the Airflow. So we have a Mesos cluster running on AWS with around 16 different nodes. So we allowed the Airflow scheduler to spawn the containers on a Mesos cluster automatically whenever it sees a new job. Again, each Docker container required required one CPU and around 1 gig of memory. So in-house we have around 500 CPUs and most of them are empty. At least the utilization was around 30%. So we could use another 70% just to run all of the other Docker containers. And once each Docker container again is looking for data from S3 bucket, training the model, and then we had to process the model somewhere. So we did process the model back to the S3 bucket. And again, there are multiple levels of persistence we do. We not only persist the machine learning model, we also do persist the feature selection model, scalars, and what are the columns which are very, very important for doing the weather prediction for that particular weather attribute or weather station. And the missing piece, how do you connect your code to the Airflow scheduler? This was not so well defined within the Airflow infrastructure, so we spent a lot of time writing git sync between our GitHub repository to the Airflow directory. So we defined a continuous integration pipeline which was running all the tests and copying the DAGs which were passing the tests to the Airflow DAG folder. Once the DAG was sitting on the DAG folder for Airflow, it spawned the results on the Mesos cluster and kept running the jobs and did process the models back to the S3 bucket. And this is all good. We train the model, we process the model on the S3 bucket. Now, how do we verify that? So we also wanted to have a thin framework which is sitting on top of everything to do the verification. And the model, this is probably the most significant part of the entire infrastructure. We have an idea, we came up with this job, which is nothing but a DAG, and it's running on the Mesos cluster. Now, how do we verify, right? So the workflow was once we deploy the DAG to the Airflow cluster, we verify the model, and then iteratively improve the model, and then deploy it again. So what was the infrastructure within the verification? Once we have the models persisting in the S3 bucket, we built a small microservice using Flask, which is written in, which is a Python microservice, micro framework, sorry, and we Dockerized it and ran it in the same Mesos cluster, and then dished out the operational forecast using JSON-LD using REST API. Now, what are the verification metrics for the modeling? We did a plethora of verification. Sorry, we did a plethora of verification metrics. These are only subset, basic ones, absolute error, root mean square error, mean error, skill scores, density functions, percentile graphs. So what you look over here is a D3 visualization from the microservice, where you see the top, all the top lines in the line graph are the data which we receive, and the bottom ones are the two models, the current one and the new one. So you can see the mean absolute error is lower and lower, so that's a very good sign. And here's the probability density function for the different models. And here's one of the percentile graphs for the temperature for the new model, how the errors are distributed in the spectrum. And if you want to know more about this verification framework, you can always stop by at MeteoGroup booth over here, and we can always run through a demo. So what were the lessons learned? We spent a lot of time designing the system, and in the beginning of the system, we really wanted to see, we had few objectives itself, and one of them was to moving the solution to the cloud. And right now, we have all the data persisting in around S3. The footprint of the data is around 1 petabyte for this particular model. And we run a Mesos cluster on the EC2 instances. And we use Elastic Cache for queuing up the task for Airflow. Making it transparent, yes, we have a verification service. If you want to see for a particular region in the world, on why it's working and how it's doing. We can always do that using the microservice. And how scalable is it? So we are only limited by the Mesos cluster, number of CPUs available in the Mesos cluster. Ideally, if you have around 47,000 CPUs, you can run the entire model in less than 10 minutes. But obviously, nobody's going to give you 47,000 CPUs unless you're Google or Facebook. So we had to use the existing CPUs and split the task and queue them up. And so current model uses takes around 1 month to train. And we brought that down to around 5 hours. And we generally schedule it at the end of the evening. And the next day we are back in the office. We have the beautiful results waiting for us. And improving the forecasting accuracy, we are on par or better for almost all the locations throughout the world, but we are just not happy yet. We really want to go further down the line and do a bit more advanced modeling. We are definitely looking into deep learning, but again, we really want to be pragmatic. We will not be using unless we really need it. And what are the improvements we really want to make? So right now we are training the data for 47,000 locations across the world, but we really wanted to do hyperlocal. So let's say any point in the world, at any given latitude or longitude, if I want the data, if I want the weather forecast, I should literally run the model on the fly and give the data back to the user. That's one of the things which we're really looking forward to. And the other one was Amazon Lambda integration. So for the forecasting part, since we have 47,000 different locations, we want to trigger the forecasting itself using Amazon Lambda. Again, we can trigger each Lambda function for a given location and get the results back within a matter of seconds. And we definitely want to iterate for more accuracy. Again, we have lots of meteorologists in-house who are working on this particular project. So we want to iteratively get better. Those are the improvements definitely we want to make. So that's part of my talk, and I will definitely take questions now.
Thank you for your talk. I do have a couple of questions here. Can anyone hear me all right? Okay, cool. Lots of them are about data quality. So how do you address historical extremes from 3 years of historical data?
Yes, that's a very good question. So again, as you can imagine, the seasonal data is, we obviously want to cover all the seasons. And if you, for the meteorology itself, every 2 years, there are certain events which do happen. So it's hard to recognize outliers, but at the same time, we have to maintain the quality of the data. We have a pipeline which addresses the outliers using basic interpolation techniques and sees what are the outliers within the data. We generally remove around 5% of the data using these techniques for now. Yeah, but again, it's a huge. At least we spent around 70% of the data just doing data wrangling rather than actual modeling. So it's a big part of our pipeline.
right ones to insert into the model with missing values?
Right. So this is a very interesting question. We can always use just basic modeling techniques using without knowing the subject matter expertise. But we always take into consideration subject matter expertise on seeing what the pressure level of the data which is missing and seeing if what is the available data within the same pressure level. So once we get that details, we try to interpolate using nearest neighbor interpolation for now is one of the techniques we use. We are also doing lots of spline interpolation. Again, this depends upon what are the weather predictors we are forecasting for. Yeah.
Okay. Obviously, there's a big set of data that you have there. So the question is, on what data do developers work? The complete productive data or some subset of test data? If test data, how do you generate it?
Interesting question. So to be honest, when I started it using on my computer, I did a random selection of 500 locations out of 47,000 locations, which was a bad idea because if you take a location, if you take given area, atmosphere, it depends drastically from other area. So instead of doing testing on a given subset of stations, we thought we should do verification across all of the 47,000 locations. Again, the complication is getting the results out of the data. But just for doing the selections for 500 stations, I used random number generator and picked up the stations using random number. So no two iterations were same.
Okay, now for something completely different, the cluster. If a node inside the cluster fails, and because of that the deployed job fails also, will the job be rescheduled, and do you have long-running jobs?
Well, a great question. Airflow comes with an existing functionality where if, let's say, a job fails, you can automatically define how many number of tries you can give the job. Let's say it failed because of some node went down or something. You can define saying that, okay, just give it one more try. And you can always define this on the DAG itself. And generally, it tries to run it again. And if it fails again, it will mark as failed. And you have this nice user interface where you can look at and see what are the jobs which are failing. And you can also look at the logs on the UI.
Okay, I have one last question here. Otherwise, if you then still have questions, we can, because we still have some time, we can answer them here. Question. Did you think about deploying trained models described in PMML with some performant language?
Oh, well, we didn't get there yet. But that's been on one of the things to do for now. But let's see how it works out.